Hi guys, welcome back to MATHerrific. My name is Roy P. Karangian. For today's video, we're going to talk about the different types of discontinuity. But before I start, please don't forget to like and share this video and hit the notification bell to keep you updated on our latest video. Okay, there are two types of discontinuity: removable discontinuity and essential discontinuity, which has two cases. The first case is jump essential discontinuity, and the second one is infinite essential discontinuity. Let's talk about removable discontinuity. A function f of x is said to have a removable discontinuity at x is equal to c if the limit of our function f of x as x approaches c exists, and it's either f of c does not exist or f of x is not equal to the limit of our function f of x as x approaches c. It is said to be removable because the discontinuity may be removed by redefining f of c so that it will be equal to the limit of our function f of x as x approaches c. In other words, if the limit of our function f of x as x approaches c is equal to L, a removable discontinuity is remedied by the redefinition. So let f of c equal to L. Take a look at the graph. Our function is g of x. The discontinuity of g at a point x is equal to 1 is manifested by the hole in the graph of y is equal to g of x at the point 1, 2. This is due to the fact that f of 1 is equal to 1 and not 2, while the limit of our function g of x as x approaches 1 is equal to 2. We now demonstrate how this kind of discontinuity may be removed, so let g of 1 be equal to 2. This is called a redefinition of g at x is equal to 1. The redefinition results in a transfer of a point 1, 1 to the hole of 1, 2. In effect, the hole is filled and the discontinuity is removed. This is why the discontinuity is also called a hole discontinuity. Let's go back to the graph of g of x and see how redefining f of 1 to be 2 removes the discontinuity. Okay, revises the function to its continuous counterpart, so it becomes g of x is equal to the g of x if x is not equal to 1, and 2 if x is equal to 1. And the last type, the essential discontinuity. A function f of x is said to have essential discontinuity at x is equal to c if the limit of our function f of x as x approaches c does not exist. Case 1. If a function f of x, limit of our function f of x as x approaches c does not exist because the limits from the left and right of x is equal to c both exist but are not equal. That's it. The limit of our function f of x as x approaches c to the left is equal to L, and the limit of our function f of x as x approaches c from the right is equal to m, where m and L are not equal. Then f is said to have a jump essential discontinuity at x is equal to c. Let's have an example. So our h of x is equal to x plus 1 if x is less than 4, and square of x minus 4 plus 3 if x is greater than or equal to 4. So if you try to graph the function, it look like this. and then analyze both from the left and from the right. So the limit of our function h of x as x approaches 4 from the left is 5, and the limit of our function h of x as x approaches 4 from the left, from the right, is equal to 3. If you try to notice, the limit from the left is 5 and the limit from the right is 3, and they are not equal. Therefore, the given function h of x is considered as the jump essential discontinuity. Now to case number 2. If a function f of x is such that the limit of our function f of x as x approaches c does not exist because either the limit of our function f of c from the left is negative infinity, or the limit of our function f of x as x approaches c from the left is positive infinity, or the limit of our function f of x as x approaches c from the right is negative infinity, or the limit of our function f of x as x approaches c from the right is positive infinity, then our function f of x is said to have an infinite discontinuity at x is equal to c. And let's have an example. Our function is j of x, which is equal to 1 over x. Let's examine the graph. The limit of our function 1 over x as x approaches 0 from the left is going to negative infinity, and the limit of our function 1 over x as x approaches 0 from the right is positive infinity, and it satisfies two of the conditions. Therefore, the function j of x, or the limit of our function j of x as x approaches 0, is an example of infinite essential discontinuity. Here is the flowchart which help evaluate whether a function is continuous or not at point C. But before that, make sure that the function exists on the open interval containing C except at C. Question: does limit of our function f of x as x approaches C exist? If your answer is yes, is that equal to f of C? If yes, f is continuous at C. If no, f has a removable discontinuity at C. If your answer a while ago, no, to the question does the limit of our function f of x as x approaches C exist, do the one-sided limits exist but are unequal? If your answer is no, f has an infinite essential discontinuity. If your answer is yes, f has a jump essential discontinuity. And that's the end of my presentation. Thanks for watching. See you again on my next video. Stay safe everyone. Bye!